Okie doke, so some add-on to TSTE27, the first lecture. We ended up the ordinary lecture by coming to some different ways of writing the transfer function of a common source stage, and then we had a couple of derivations from that. So we had a transistor stage with an active load like this. So we have a PMOS on top and a bias voltage, a constant bias voltage, and then we have our input signal, and then we had a load capacitance CL. We have V out and V in, and then we did some derivations here with a small signal schematic, and eventually we came up with A of S is equal to V out over V in of S, if we like. And we found this expression here, which was GMN divided by GN plus GP divided by, and then we had a minus because it's a common source which inverts the output. And then we have 1 plus S over GN plus GP over CL. So this is Bode's normal form, or at least in Swedish, BNF, where we can write the transfer function as a DC gain and then 1 plus the pole. And if we would have more poles, that we do like 1 plus S over P1, for example, times 1 over S over P2, etc. So that's the typical way of writing it, and the nice thing is that we can identify directly the different terms. So for example, this is my gain, my DC gain A0, and this is my pole, my dominant pole P1. And we mentioned we had a transfer function like this in the Bode plot, so absolute of A, and A0 is here, and then we have P1 here, and omega UG, the unity gain frequency at which we don't have any gain anymore. So beyond this point, it's not an amplifier anymore. Here we have gain, here we don't. We can look at this expression. So if we write this in a slightly more compact way, A of S is equal to A0, and I ignore the minus for now, 1 plus S over P1. And I want to know what happens when this is equal to 1. So when is the absolute A of S equal to 1? Well, then that's when we have A0 1 plus S over P1 squared even equal to 1 squared, which is obviously 1. And that happens if we reorder the equation here. We have A0 squared is equal to 1 plus, and then S is my frequency variable, so that's simply going to be omega squared divided by P1 squared. And then if we look at this diagram here, this 1 is negligible compared to this term, typically. So I can say for large omega, I mean P1 is here, omega UG, the omega at which we are looking for the intersection here of the x-axis. That's a number which is much, much higher than P1. So this term is going to be large, that's going to be small, at least as long as A0 is pretty large. So that's approximately equal to omega squared over P1 squared, and that implies that omega is equal to A0 P1. And that's the expression we derived last time. And that's the bandwidth gain trade-off. So let's look a little bit on the equations we get. So A0, that's equal to, ignore the minus for now, that's GMN divided by GN plus GP, small signal characteristics. And GMN we said was 2ID divided by delta V or VF. like this, divided by lambda n times I dq. Let's add the q here for the quiescent point, just to be overambitious. And then plus lambda p times I dq, like that. And then we find that we can get rid of these guys. So what are we left with? We're left with 1 over, and then we have delta v, I ignore the q for now, and then I have lambda n plus lambda p divided by 2. And if we look at this, this is the mean value of these two guys, lambda n and lambda p. So that's, we just say is 1 over lambda delta v then, where we have some sort of generic lambda. And we knew since earlier that lambda is inversely proportional to the channel length of the devices. So we have a very compact way of saying that the DC gain A0 is equal to a term which is 1 over lambda delta V, the effective gate voltage. Gate voltage. And that's essentially the level above the threshold voltage that we select as a DC operating point at the input. Let's look at the other parameters. We have G out, which I introduced now, which is GP plus GN. So that's my output conductance. And that's now obviously lambda IDQ P plus lambda n IDQ. And we find that the pole P1 is equal to IDQ times lambda P plus lambda n divided by C load. And that's equal to, we'll just introduce a 2 here and a 2 there. So that's equal to 2 IDQ lambda divided by CL. So I take the average value here again. And then I get the term, and I can identify components here also shortly. Let's look at omega UG. So that's according to the equations we had. A0 times P1. So that's simply GMN divided by G out times G out divided by CL. Get rid of those guys. And we see it's GMN over CL. Or if we like, if we want to put some numbers on this, for example 2IDQ divided by delta V times CL. So now it's sort of up to you as a designer. We have P1 and A0. We have different options. I might want to have a slightly lower gain but a higher bandwidth P on prim. I might even try to extend my overall bandwidth, my overall omega UG, by pushing the gain curve like this. So what are the impact of the different parameters? So what could I do, for example? Well, let's look at these guys again on a slightly different page. So I have A0, that's 1 over lambda delta V. I have P1 equal to, just refresh that, 2 IDQ lambda, 2 IDQ lambda divided by CL, and I have omega UG equal to 2 IDQ delta VCL. So, for example, I could increase the current, could be one way of doing it. IDQ, increase. What happens? Well, of course, quite a few of these parameters are following each other. I mean, we have, for example, the equation saying that alpha delta v squared, like this, which means that dependent on, you know, if we increase ID, okay, maybe we need to increase the size of the transistor, or we need to increase the delta V. What happens if I increase the delta V? Well, if I increase delta V, gain reduces, and also this term will decrease. So one has to find the sort of trade-off between all these components or all these values. We could, for example, also decrease lambda. So the mechanism would be to increase the channel length L, because lambda is proportional, inversely proportional to the length. That would increase the DC gain, but in that turn would decrease the P1, and this would not be affected per se. So it's important to understand how all these parameters are connected to each other, and there is no sort of direct way of isolating them from each other. Also the fact that we change lambda and change L, if we look at this expression here, ID is equal to mu naught Cox divided by 2 W over L times delta V squared. So if I increase the L, I also see that I reduce the ID. If I reduce the ID and reduce the lambda, both these two terms will decrease. And P1 will decrease, this will increase, but then this guy will also potentially decrease, because I have two terms here decreasing and only one term here increasing, etc. So somehow we need to work on this and understand the trade-offs between them and cost functions. What should we sacrifice in this equation in order to maximize the gain, the bandwidth, or the unity gain frequency? How do they keep up with each other?